So, probability with a little bit of a difference here. Have you ever done this before, converted a Venn diagram into a probability tree? Let's see how you get on with this one. So it should be fairly clear that we've got two events here, and we've got four possible combinations of outcomes. So the basic structure of the probability tree should be fairly clear. So hopefully you would have got that. But then the question becomes, well, what are these branches then? And you may have possibly considered putting an A here and a B there. That's one possible scenario. But the problem is that our convention when we're drawing probability trees is that at every branch here, when we look at these two possible branches, that the probabilities of those two events add up to 1. But that's not necessarily the case. It may be the case, but we don't know at this stage. So we can't assume that. So I don't think this particular layout is going to help us at all. So instead, I'm putting A and not A as the first two options, the first event, and then B and not B as the subsequent options on the second event. So now we can put some information on the from the Venn diagram onto this table, onto this tree diagram. So first we can look at this 0.42. So that 0.42 is in A but not in B. So that's this going that path through the tree, whereas the 0.12 is in B but not in A, so that's this path through the probability tree. So that's what it looks like when it's drawn neatly. So now I need to do some work, some algebraic work. So what I'm going to do is to define the probability of A and probability of B as letters, just to make my life a little easier. So if we let the probability of A equal little a and the probability of B equal little b, then what we're saying here, this 0.42, is A times 1 minus B. So A times 1 minus B is 0.42. Doing something similar on the with the other number, the 0.12, we're saying 1 minus A times B is 0.12. So there's that equation. So what have we got? We've got simultaneous equations. Hang on, this is a probability question. Simultaneous equations. But there we are. And what I'm going to do is simply to subtract the second equation from the first. So when I do that, I get A minus B is equal to 0.3. So A, for example, equals 0.3 plus B. And if I put that back into there, I get 0.3 plus B times 1 minus B equals 0.42. Goodness, not only have we got simultaneous equations, we've now got a quadratic equation for a probability question. Anyhow, we can solve this. I'm not going to go through the detail of solving this. Most of you should be up to that by now. And we get 2 positive values for B. So both of these are in contention at the moment. So 2 possible values for B. If we then calculate the value of A for each of those, which is just adding 0.3 on, we get A is 0.7 or 0.6. But how do we choose between these two values? Is it the 2 green values or the 2 red values? Well, we've got this little piece of information in the question here. The probability of A and B is greater than 0.2. So in the notation of A and B, that's just A times B. because A and B are independent. So that means that A times B must be greater than 0.2. So AB here is either 0.28 or 0.18. So those are the values that are of interest to us. So we can then put the value for A in, the probability of A of 0.7, which means that not A is 0.3, and then the values for B, 0.4, which means not B is 0.6, and those again are repeated again because A and B are independent. We can complete the probability tree now by multiplying the rest of the values, and always when you're doing a probability tree, check that the values add up to 1, which they do. So there may be another method of doing this, I'm not sure. Some of you may have thought of a different way, but hopefully nevertheless you got the same answer that I did, which is this is the answer here, the tree diagram. That's the answer to the question. So if you got the same answer, then well done.